topic for this video is the nature of mathematical reasoning. Our learning objectives will be to identify two types of reasoning, use inductive reasoning to make conjectures. We'll talk about how to find a counterexample to disprove a conjecture. We'll explain the difference between inductive and deductive reasoning. And then we'll go over how to use deductive reasoning to prove a conjecture. So let's begin by defining the term inductive reasoning. Inductive reasoning. Inductive reasoning is the process of reasoning that arrives at a general conclusion based on the observation of specific examples. For example, suppose that your instructor gives a surprise quiz every Friday for the first 4 weeks of your math class. At this point, you might make a conjecture. And a conjecture is essentially an educated guess. So we'll make an educated guess that you'll have a surprise quiz the next Friday as well. Let's go over how we might use inductive reasoning to find a pattern in a sequence of numbers. Let's suppose that a game show host provides the following string of numbers: 1, 2, 4, 5, 7, 8, 10. The ... indicates that there's a pattern that continues indefinitely here. And let's say that the game show host promises the first contestant who can continue the pattern and figure out the next three numbers in the sequence will win $4,000 and an 18-month supply of Rice-A-Roni, the San Francisco treat. So let's use inductive reasoning to find a correct answer, and then let's talk a little bit about how confident we are in the answer. Would we be 100% confident or less than that? So let's start by trying to identify a pattern. To find patterns in a string of numbers, scroll down here, it's often helpful to think about operations that can turn a number into the next one. In this case, we can use addition, the mathematical operation of addition, to help us find a regular pattern. To do that, let's start with the known numbers. I'm just going to write them down here. 1, 2, 4, 5, 7, 8, 10. And let's think about using the mathematical operation of addition. What would we need to do to go from the first number in the sequence to the second number in the sequence? That's going from a 1 to a 2. That requires adding 1. Going from a 2 to a 4, well, that requires adding 2. Going from a 4 to a 5 requires adding 1. From a 5 to a 7 requires adding 2. From a 7 to an 8, that requires adding 1. From an 8 to a 10 requires adding 2. So the pattern seems to be to add 1, and then add 2, and then add 1, and then add 2, etc. So what would be a reasonable conjecture for the next three numbers? Well, if we continue the same pattern, what we would need to do next is add 1, which gives us an 11. Then we would need to add 2, which gives us a 13. And then add 1, which would give us a 14. So a reasonable conjecture for the next three numbers in the sequence would be 11, 13, and 14. Now, how confident can I be in this answer? I certainly like this answer a lot, but I cannot say that I am 100% confident. To obtain this result, I made an educated guess based on just 7 numbers. There's no guarantee that this is the only correct answer, or that this pattern continues indefinitely, right? So I made this educated guess based off of the available data. But that does not prove that this is the only correct answer or that this sequence will continue indefinitely. Let's do another example. This time, instead of using a sequence of numbers, we'll use a sequence of pictures. So we want to make a reasonable conjecture for the next figure in the sequence. So let's take a look at what we observe here. So in the first four figures, we see there's kind of a circular part down here and a flat part up here. In the first figure, the flat part is on top. And then over here, the flat part is facing to the right, and then down, and then to the left. And then furthermore, in the first four figures, we see that there's a small solid circle in the middle of each figure. Then the sequence repeats. And the only difference is that this time the figures have open circles in the middle. Otherwise, the figures look the same, right? So the same sequence. The flat part starts on top, then it moves to the right, and then it moves down. So for the next figure in the sequence, it would make sense that we would see a figure where the flat part faces to the left, and it has an open circle. Something like this. Right? That would make sense based off of what we observe. So again, that's an example of inductive reasoning, reaching a conclusion based off of a limited amount of data. Let's look at another example of using inductive reasoning to make a conjecture. So, when two numbers are added, will the result always be an even number? Okay, so we want to use inductive reasoning to make a conjecture. Okay, so let's do that, and then we'll come back and look at that second question. So our conjecture is essentially when you add two odd numbers, the result is always even. So what we can do is we can try several specific examples of adding two odd numbers. So let's try 3 plus 7. That gives me 10. Let's try 25 plus 5. That gives me 30. Let's try 5 plus 9. That gives me 14. Notice in all three of these cases, the result is an even number, right? So far, the evidence seems to support our conjecture. Let's try a few more. 1 plus 27 gives me 28. That's an even number. Let's try 19 plus 9, which also gives me 28. That's an even number. Let's try 21 plus 33, which gives me 54. That is also an even number. So in all the specific cases that we've tried, we see that every time we've added two odd numbers, in every case we've gotten an even number. So it seems reasonable to conclude that the sum of two odd numbers will be an even number. But what about that second question there, part B? How many pairs of numbers would you need to try in order to be certain that your conjecture is true? Well, this is kind of a trick question, because to prove the conjecture is true, we would actually have to try every single possible way of adding two odd numbers. And it's just not possible to do that because there's an infinite number of numbers, right? There's no way we could try every possible scenario because numbers are infinite, right? We could try specific examples all day and always get an even sum, but that can never guarantee that it will always happen. To prove that a conjecture is true, we generally cannot rely on inductive reasoning. We have to use a type of reasoning called deductive reasoning, which we'll take a look at in just a little bit. But before we do that, let's go over another example. And we're going to talk about an example that involves dividing numbers. So I want to define the term divisible. We say that one number is divisible by another number if the remainder is 0 after dividing. For example, 16 is divisible by 8 because 16 divided by 8 has a remainder of 0. But 17 is not divisible by 8 because 17 divided by 8 has a remainder of 1. So, with this idea in mind, let's take a look at our next example. Use inductive reasoning to decide if the following conjecture is likely to be true. Any 4-digit number is divisible by 11 if the difference between the sum of the first and third digits and the sum of the second and fourth digits is divisible by 11. Well, let's make up a few examples. Let's see, let's start with 1,738. So I need to find the sum of the first and third digits. That would be 1 plus 3 equals 4. And then we'll look at the sum of the second and fourth digits. 7 plus 8 equals 15. The difference between those numbers is 15 minus 4 equals 11. 11 is definitely divisible by 11. So if the conjecture is true, the original number should also be divisible by 11. Okay? So the original number is 1,738. If I divide that by 11, you can use a calculator here to make your work a little bit easier if you want to. I get 158. No remainder. So this specific case does indeed support our conjecture. Let's try another case. Let's try 9,273. Okay, so if I take the sum of the first and third digits, I get 9 plus 7, which equals 16. If I take the sum of the second and fourth digits, I get 2 plus 3, which equals 5. And if I subtract 16 and 5, I get 11, which is definitely divisible by 11. So, if the conjecture is true, then the original number, 9,273, should also be divisible by 11. And in fact it is, because if you divide that by 11, you get 843 with no remainder. We'll check one more example. Let's try 7,161. So if I add the first and the third digits, I get 7 plus 6 equals 13. If I add the second and fourth digits, I get 1 plus 1, which equals 2. Well, 13 minus 2 equals 11. So if the conjecture is true, then the original number should be divisible by 11. So let's see if it is. 7,161. If I divide that by 11, I get 651 with no remainder. So the conjecture is true for this example as well. So while we can't be positive based on 3 examples, inductive reasoning does indicate that the conjecture is likely to be true. We cannot say that it's definitely true based off of only 3 examples, but the evidence that we have does seem to support the conjecture. Now, while it is not often easy to prove that a conjecture is true, it's actually much simpler to prove that one is false. All you need is to find one specific example that contradicts the conjecture. This is known as a counterexample. So let's look at an example involving finding a counterexample. Find a counterexample that proves the conjecture below is false. The conjecture: a number is divisible by 3 if the last 2 digits are divisible by 3. So let's test this conjecture with a few specific cases. We'll pick, come down here, we'll pick a few numbers at random whose last 2 digits are divisible by 3. And then we'll divide the original number by 3 and see if there's a remainder. So my first specific case, I've got 1,527. The last 2 digits are 27. That's divisible by 3 because if I divide by 3, I get 9. Does that, so if the conjecture is true, then the original number should also be divisible by 3. So we've got 1,527. If I divide that by 3, I get 509. So here we have one specific case that does support the conjecture. Let's try another case. Let's try 11,745. The last 2 digits are 45. They are divisible by 3 because that result is 15. If the conjecture is true, then the original number, 11,745, should also be divisible by 3. And if I do this, I get 3,915. At this point, we might start to suspect that the conjecture is true. But again, we cannot prove that a conjecture is true based off of only a couple of specific cases. We've only checked 2 cases, and there are literally infinitely many possibilities. Now, we can prove a conjecture false by demonstrating one counterexample, right? One situation where the conjecture is false. So let's try one more scenario. Let's try the number 1,136. The last 2 digits are 36. And if I divide by 3, that's divisible by 3, right? That result is 12. So what about the original number, 1,136 divided by 3? Well, if you do this calculation, you would actually get 378 and 2/3. It does not come out even. There is a remainder, right? So this is a counterexample. And this single counterexample shows that the conjecture is false. So, word of caution. One counterexample is enough to show that a conjecture is false. But one positive example is never enough to show that a conjecture is true. In fact, in most cases, even 100 positive examples wouldn't do it. That's why we need a different type of reasoning to prove a conjecture true. So let's start talking about deductive reasoning. Deductive reasoning is the process of reasoning that arrives at a conclusion based on previously accepted general statements. It's based on overall rules, not specific examples. Let's consider an example. At many colleges, a student has to be registered for at least 12 hours to be considered full-time. So we accept the statement, a student is full-time if they are registered for at least 12 hours, as true. If we're then told that a particular student has full-time status, we can conclude that the student is registered for at least 12 hours. The key is that we can be positive that this is true. On the other hand, you might have 10 friends who are full-time students, and all of them might be taking 15 or more hours of classes. If you concluded that full-time means more than 14 hours, you'd be using inductive reasoning, not deductive. And in this case, you'd probably be wrong, right? But the definition of full-time as being at least 12 hours, that's a general rule, right? It's a specific rule. So in our next example, we will look at an incredibly important aspect of these types of reasoning. We'll use inductive reasoning to make a conjecture, and then we'll use deductive reasoning to prove it. All right, so consider the following problem. Think of any number, multiply that number by 2, and then add 6 and divide the result by 2. Next, subtract the original number. What is the result? We'll start off by using inductive reasoning to make a conjecture for the answer, and then we'll use deductive reasoning to prove the conjecture. So for part A, inductive reasoning will involve picking a few specific cases and going through the process and seeing what happens. Okay, so let's just pick a number. Let's say the number 12. And we want to go through the steps described. We start by multiplying the number by 2. So we do 2 times 12. And that gives us 24. The next step is to add 6. 24 plus 6 equals 30. The next step is to divide by 2. 30 divided by 2 equals 15. And finally, the last step is to subtract the original number. 15 minus 12 equals 3. So our final result is 3. Let's try it again. Again, we're just picking numbers at random. Let's try the number 5. Step 1, multiply by 2. 2 times 5 equals 10. Add 6. 10 plus 6 equals 16. Divide by 2. 16 divided by 2 equals 8. Subtract the original number. 8 minus 5 equals 3. So we picked two numbers at random. We went through the steps, and in both cases, we got 3 as our final result. Let's try one more specific case. Let's try 43. Step 1, multiply by 2. 2 times 43 equals 86. Add 6. 86 plus 6 equals 92. Divide by 2. 92 divided by 2 equals 46. Subtract the original number. 46 minus 43 equals 3. At this point, we may be tempted to conclude that the result is always 3. But this is just a conjecture. It's an educated guess. We've only tried 3 of infinitely many possible numbers. Not to mention the fact that we've chosen only whole numbers. What about decimals, fractions, negative numbers? As usual, when using inductive reasoning, we can't be completely sure that our conjecture is always true. But at this point, it does seem like it would at least be worth the effort to see if we can prove that our conjecture is true. The evidence that we have so far does seem to support the conjecture that the result is always 3 if we do this process. So how would we use deductive reasoning? Okay. So the problem with the inductive approach is that it requires using specific numbers. And we know that we can't check every possible number. So instead, we'll choose an arbitrary number, and we'll use a letter to represent that number. Now, we could choose any letter we want to, but in this case, I'm going to let A represent my arbitrary number, okay? So think of that as standing in for any old number, right? So A could represent or be replaced with any number. So if we can show that the result is 3 in this case, that will tell us that the result is true for every number. So we're going to be doing the exact same operations, but this time just on an arbitrary number a. Now, this will require some basic algebra skills. So let's do it. First step, multiply by 2. So that would be 2 times a, which we represent as 2a. Add 6. That would be 2a plus 6. Divide that result by 2. Okay, this is where some algebra skills come in handy. So we've got 2a plus 6 divided by 2. But this can be written as 2a over 2 plus 6 over 2, two separate fractions. In this case, the 2's just cancel, leaving me with just an a. And for the second fraction, I've got 6 divided by 2, which is just 3. So that simplifies down to a plus 3. Now subtract the original number. Well, the original number is just a. So I've got a plus 3 minus a. What is this result? I've got an a. I'm adding 3 things together, right? Well, I've got an a, I'm adding 3, and then I'm subtracting a. So a minus a, those just become 0. They cancel each other out, and the result is just 3. So we went through the same series of steps using an arbitrary number, and we still got 3. Keep in mind that a can be replaced with any number, any possible number. So this proves that the conjecture is true. Right? This is an example of using deductive reasoning. And using deductive reasoning for a general situation proves the conjecture is true. Whereas inductive reasoning, where we just test specific cases, shows evidence to support the conjecture, but it's insufficient to prove that it's true. Let's look at another example. Use inductive reasoning to arrive at a general conclusion, and then prove your conclusion is true by using deductive reasoning. So here's the process. We will pick a number, we will add 50, we'll multiply by 2, and we'll subtract the original number, and we'll look at the result. So we will start with some specific cases, and we'll make a conjecture. And then we'll use deductive reasoning to try to prove our conjecture. So let's start with the number 12. The first step is to add 50. 12 plus 50 is 62. The next step is to multiply by 2. 62 times 2 is equal to 124. The next step is to subtract the original number. 124 minus 12 is equal to 112. So my result is 112. Let's try it for another number. Let's try the number 50. First step is to add 50. So 50 plus 50 equals 100. Then we'll multiply by 2. 100 times 2 equals 200. Then we'll subtract the original number. 200 minus 50 equals 150. Okay, based off of these two results, we can form a conjecture. And a reasonable conjecture would be that the final answer is 100 more than the original number. That's our conjecture, or our educated guess, that every time you pick a number and go through these steps, you will end up with a result that is 100 more than the original number. If we we see that happened with the two specific cases that we tried, right? The first case, we started with 12, we finished with 112. The second case, we started with 50, and we ended with 150. Let's see if we can prove this conjecture using deductive reasoning. And we'll do the same idea that we did in example 6. We're going to choose an arbitrary number. We'll call it A. And we'll go through the same series of steps. The first step is to add 50, right? So if I add 50, I get A plus 50. The second step is to multiply by 2. So that would be 2 times A plus 50. And I can, this is a rule of algebra, I can apply the distributive property, and I can multiply that 2 by each of the terms inside the parentheses. So this becomes 2A plus 100. Then I can subtract the original number. So that would be 2A plus 100, and the original number is A, so I do minus A. Well, 2A minus A is just A, so I end up with A plus 100. And that proves that our conjecture is right. The final answer is always 100 more than the original number, because if I start with some arbitrary number, which we call A, and go through the exact same process, the result is A plus 100, right? Keep in mind that A can be replaced with any old number, positive, negative, decimal, fraction, and the result would always be the same. The final result would always be 100 more than the original result. So our conjecture is right. Okay, let's wrap this up with a couple more examples. Comparing inductive and deductive reasoning. Let's consider this scenario. The last 6 times we played our arch rival in football, we won, so I know we're going to win on Saturday. Is this an example of inductive or deductive reasoning? Well, this conclusion is based on 6 specific occurrences. It's not based on a general rule that we know to be true. In fact, we know that no team wins every game, right? So this is an example of inductive reasoning. If you won the last 6 times, that does not mean you're going to win the next time, right? So it's inductive reasoning. And then one more example. The syllabus states that any final average between 80 and 90% will result in a B. If I get 78% on my final, my overall average will be 80.1%, so I'll get a B. Did I use inductive or deductive reasoning? So we're talking here about a specific person's grade, but the conclusion that he'll get a B is based on a general rule, right? The rule is that all scores in the 80s earn a B. So this is an example of deductive reasoning, right? We concluded that your final grade will be a B because your overall average is 80%, and that's consistent with a general rule, right? So this is an example of deductive reasoning. Okay, so remember that both inductive reasoning and deductive reasoning are useful tools for problem solving, but the biggest difference between them is that conclusions drawn from inductive reasoning, no matter how reasonable, are still at least somewhat uncertain. But conclusions drawn by using deductive reasoning can be considered definitely true, as long as the general rules used to draw the conclusion are known to be true.